and gentlemen, boys and girls, everybody go, shh. Okay. Okay. So John and everybody be quiet, please. Before I forget, last month, I forgot to announce this month's speaker. So the first thing I'm going to do is announce that our next meeting is late in May. Let me pull it up right now. Does anybody have the date handy? It's May 22nd. We do not have a speaker for it yet. However, I am currently a person at JPL who does optical navigation at JPL. He worked on the New Horizons project and also on the DART mission. And so if you've ever wondered, how do they do navigation through the solar system? This is a talk to watch for. And so he will probably be our speaker for that meeting. I'm also working on getting Dr. Kevin Hand, who's the principal investigator from the Europa mission, to speak to us, but I'm having some trouble communicating with him. And watch also, I'm going to be chasing after Dr. Dante Loretta, who is the principal investigator for the OSIRIS-X mission, which brought back samples from the asteroid that turned out to be very rich in amino acids, both left-handed and right-handed. Very, very exciting discovery. So watch for that as well. So that's what's going on right now. And by the way, one other thing I want to say is, for those of you that are out there in the internet land watching us remotely, the disadvantage of that is that every meeting, practically, my wife brings some absolutely incredibly delicious baked item to the meeting. And today she has brought chocolate flan cake. Absolutely incredible. So that's a real incentive for you guys to attend in person rather than online. So that's all I want to say about that stuff. And then I want to talk about tonight's speaker. Forgive me. I'm very excited today because I got to speak both in German and in Portuguese, which really got me very happy. And tonight's speaker is Dr. Milo Buitrago-Casas.
Mm-hmm.
Okay. And he's a research scientist at the Space Science Lab in UC Berkeley. And Milo, you're a member of EAS, are you not?
Yeah.
Yeah. How long have you been a member?
Probably like for 7 years or so.
Wow. We are honored to have you as our member. Is your wife a member too? Do you have a family membership? Oh, good.
She's gonna be soon.
Anyway, so we have really, when you come to a meeting, you look around you, we have some really remarkable members. I mean, they're just not like regular folks. They do some amazing things. They may be amateur astronomers, but they're also often professional something else's. And so tonight, Milo is a principal investigator, which means he's a really big shot at the NASA FOXSI sounding rocket experiment. And they're doing some really neat stuff. They are sending up sounding rockets to look at X-class solar flares and to look at X-rays, which are generally around 1 angstrom in wavelength, which is 1/10 of a nanometer, if I remember correctly. And so he's going to talk to us about this tonight. And he's also going to talk about, additionally, the Padre CubeSat, which is going to be launched aboard SpaceX in June. Let's cross our fingers that nothing explodes. Not that, SpaceX ever has explosions, but they're doing better. So this could dramatically improve our understanding of particle acceleration during these eruptive events. And anyway, so Milo is a physicist and master in astronomy, got his master's in astronomy from the Universidad Nacional de Colombia in Bogota.
That's correct.
And he got his PhD in physics from the UC Berkeley. And what did you write in when you were at Berkeley?
Where?
What? No, who was your advisor?
Oh, Stuart Bale.
Who was it?
Stuart Bale, Professor Stuart Bale.
Okay, fantastic.
The PI of field
Fantastic.
instrument on
I'm
Parker
sorry, go
Solar
ahead.
Probe. He's the PI of the field instrument on the Parker Solar Probe. I can talk a little bit
Really, on the Parker Solar Probe. Okay, which is, you're going to talk about that?
I didn't include that, but I can give another talk in the future about that.
Okay, sure. About the Parker Solar Probe?
Yeah.
You're kidding me. Okay, great. Okay. Anyway, if there are those of you that don't realize that the Parker Solar Probe is the space probe that got the closest to the sun that any space probe has ever gotten. What is the distance? It's several million miles.
It's a 9-point-something solar radii.
Okay.
That happened on last Christmas.
Okay, and the sun is slightly less than 1 million miles wide. So if it's 9 solar radii, that's approximately 9 million miles from the sun, which is incredible. And anyway, it's an incredible mission. My wife actually, you have a T-shirt for the the probe, don't you, Rebecca? She does. Anyway, she also has a T-shirt that says that NASA faked the sun landing. Anyway, so he got his PhD in physics at UC Berkeley, and he's now a research scientist at the Space Science Lab at UC Berkeley, up there on the hill. Beautiful view up there. And he's the principal investigator of NASA's FOXSI 5 sounding rocket experiment, and the instrument lead on the solar hard X-ray polarimeter that will be launched as part of NASA Padres CubeSat payload in the summer of this year. So without any further ado, Milo, big round of applause for him. Thank you very much for coming.
I think I have a mic already. Can you guys hear me okay without this?
Yeah, great.
Excellent. Cool. Okay, let me try this. So thank you, Dave. Thank you, Rebecca. And thank you all for coming, Richard, inviting me. It's an honor and a pleasure to be here. Not the first time I'm here. I've been here sharing some time with your precious telescopes on the deck. That was before the pandemic, and I don't need to speak about the pandemic because everybody lived that. I was a volunteer, like you can see some photos, like
you were operating lead?
Yeah. But that was again that's why I took some time off. Probably, well, I had to finish a PhD thesis, and then, but now I want to come back, and this is a great opportunity to just resume the activities. But yeah, no, a lot of good experiences there, and I miss that from my time here at Chabot. So here we go. So I'm here again, and thank you again, because it's really a pleasure. So what is this talk about? Well, I had to confess, like putting together the slides, because I have never given a talk combining the two instruments, Padre and FOXSI, and I had to mix some things. So in the end, I found that the best way to convey the message I want to convey today is that to show that many of us, in different ways, we dedicate our lives to look at the sun. This is a photo during one of the recent solar eclipses that many of you, I hope, enjoyed, as I did, with a group of students in Colombia. This is in Bucaramanga, Santander, in South America, Colombia, and you probably also did here. We had some telescopes, filters, and what have you, but we were looking at other stars. So from that point up to professional ways to look at the sun, this is a couple of photos from some of the latest rocket campaigns where we put together instruments optimized to look at the sun. So they are basically solar telescopes that we launched to space as sounding rockets, or now CubeSats, PhD thesis supervisor, a probe inside the sun. What you have in that photo is one of the sounding rockets. This image shows you the latest version of what we put inside that sounding rocket as a payload. You see 7 different telescopes, all of them optimized in different ways to look at the sun in X-rays. On your left, you see the rocket launch, one of the rocket launches that we did from the White Sands Missile Range in Alaska, in New Mexico. And on the right is just a common footage of the sun. So this to say, today I'm gonna invest some time in showing you how we use both FOXSI and Padre as missions to study the sun. On your left is the SolidWorks model of the payload in FOXSI, and on your right you see the same SolidWorks design of the Padre satellite. So we are studying the sun, but why to study the sun? Well, because it's our field, right? Every second, the sun emits the equivalent of 1 million times what the entire humanity is consuming today, even when you account for the new consumption of all the servers that run AI. So it is an incredible amount of energy that is being emitted from the sun. Some of us may say that we not only study the sun because it's technically useful and it has applications, but because it's beautiful. It's a source of endless inspiration. And this is one of the photos that I have taken from the sun, just like a little glance before sunset. And I bet many of you have taken even better photos like this. So again, why to study the sun? And I'm sorry for the night astronomers, but I have to say this is because you guys, I know they are very jealous at us solar astrophysicists, because this is the closest you can see your object from using the best telescopes. This is, of course, you can recognize, this is from here, from Chabot, and night astronomers, you look at your star and see a dot. In the best of the cases, you slightly see some structure that shows a disk, but we solar astrophysicists can see much, much more detail. And this that I'm showing you here is an example of the kind of images and data that we are able to record today using the best technology available. So this is an example of one of the images taken with an instrument inside a sounding rocket. This is not the one that we launched with the Space Science Lab as PI institution. This is the PI institution is Marshall, and this is the sun in UV. But you can see the amount of structure that we are able to see now. So you see that many of the filaments in here, they have substructures that we are starting to see. So we are in a golden age to look at the sun. We can see the sun also 24/7. That's another reason why night astronomers are jealous at us, because you can see the sun even at night. You can see it now, and this is roughly the sun that you could observe right now if we were in daytime. You use your eclipse glasses, and the fact that we can see it is because of the many instruments that we have around in orbit around the planet. An example is the Solar Dynamic Observatory that we have to send to space because of this reason, the Earth atmosphere. So we all know it protects us and it protects us from UV, but because it absorbs UV and X-rays, it means that to look at the sun in these very interesting wavelengths, you have to take your instrument outside the planet. And that's the reason we have to send our instrument there. This is also the sun as it looks right now, or a few hours ago when I was putting the slides finally. And you see much, much more structure. You can see, go over the Solar Dynamic Observatory website and look at the sun at different wavelengths in UV. Those are at the top, all those fake colors over there, plus this that is invisible in the continuum. These are also UV, but you can also see the sun in other different ways. This is a map of the magnetic field. This is a map also of the magnetic field, but with direction, a vector magnetogram that we call. And this is a Dopplergram. So there are many, many ways of, that we have now to see at the sun and ways to understand it as never before. This is the sun as it looks like right now. That's not the only way we can see it. We can see its effects on Earth. This was just 2 nights ago from Scotland. And I don't know if you guys were able to enjoy it. Last year, auroras that twice, we got to see twice last year, one in May and one in October, if I remember well. So I know you guys are very familiar with this, but I wanted to give like full context. All of this that we are able to see is because of the solar magnetic field. And the current model showed us that the solar interior, and we define, and it's a definition because the sun, you know, doesn't have a solid surface. We define the interior as everything below the photosphere, and the photosphere is just the layer at which the deepest layer we can see with our eyes. That light in the continuum can escape the surrounding plasma and reach our telescopes and reach Earth. So everything beneath that, you have the convective sun that goes from the surface until 70% of the solar radius. And then is there where there is a zone called the tachocline, in which we believe the magnetic field has its source. And we believe, and we have measured that its main component is a magnetic dipole, very similar to the ones that you put on your refrigerator, but with the difference that because of the differential rotation of the sun, the plasma near the belly of the sun rotates faster than the plasma at the poles. And when you account for that, then those magnetic field lines get a drag, and that drag entangle the geometry of the magnetic field lines. And those magnetic field lines, when they get unstable, they can reach the solar surface, go into the solar corona, and display all those beautiful solar loops and filaments that we can see. We are also very aware of the solar cycle. That is not other thing but how we account for the solar magnetic activity. And this is an image that I love. This is for the 25 years of SOHO, the SOHO mission. And you see how every 11 years, you see that the sun is way more active, has way more structure on its corona. That's the region that you are seeing here. And in the middle, you see that there is very little. We have different ways to look at this solar cycle. One that I love the most is this one, in which you count the number of solar flares on the disk. So this white circle represents the solar disk, and every single dot, let me go back and repeat this. Every single dot here is a solar flare that happened in here. You can see the period of time. I think, yes, this was made with solar orbiter, the Solar Dynamic Observatory observations. And if you display the heliographic latitude against time, you get this beautiful diagram, the water, I forgot the name in English, mariposa, butterfly diagram. Thank you. So this is one way of looking at that diagram. This is another way. This is more standard. So we have count the number of average number of active region on time, and you see how every 11 years you see a maximum in the number of active regions that you see over the sun. And if you plot the same heliographic latitude against time, you also see not one but several butterflies. That's not the only way to see butterflies. This is another butterfly diagram that I love, which shows the magnetic polarity. Again, the magnetic polarity in the color scale in grays here. So black is negative magnetic polarity, white is positive magnetic polarity. And I love this because this displays the real solar cycle, which is not 11 years, but it's 22 years. It takes 22 years to flip again to the original configuration of the magnetic field. So this is mainly the source of the magnetic activity that we see on the solar corona. And this is the sun as we see it in the last couple of days. So you can recognize the UV image on the background. This is a 171 Armstrong line taken by the Solar Dynamic Observatory. And then you see those lines are extrapolations of magnetic field models, just to get an idea of how the different magnetic lines are entangling together and they're reconnecting, and they are evolving on time. So because of the dynamic of that magnetic field, because of the instability of that magnetic topology or geometry, if you like, is that every so often we get to see very sudden and powerful reconnection of the magnetic field. And when that happens, is that we get this marvelous phenomena, the solar flares, that involve a wide variety of physics.
Real?
It's a footage. It's just, yeah, it's an artistic way of looking at this, but it's a good one that conveys the message of this thing emits between 10,000 to 100,000 times in 10 minutes times the the annual energy consumption of the entire humanity. So it's just between 0.1 and 1% the total energy release of the entire sun, but this is just in a couple of minutes. So there is a lot of how we understand solar flares. They happen because there is a magnetic energy built up, produced, we believe, mainly by buoyancy of the convective cells that are pulling and pulling energy from the interior of the sun into the coronal magnetic field. And then once that geometry gets very unstable, then there is a rapid release by a new reconfiguration of the magnetic geometry field. When that happens, there is particle energization, like this wording. There are all kinds of particles that get accelerated and ejected and ejected in every possible direction. And depending on their mass, their electric charge, in general, their characteristics, we'll see certain phenomena or not. There is direct plasma heating, and this is one that I like. There is energy and momentum transfer. There are new approaches, not new. Energy and momentum conservation is being for centuries out there, but this is a new avenue that we are trying to follow, just using like basic physics to understand how energy and momentum should be conserved during the time of a large flare. So that's something we are doing. And of course, waves in many kinds, that there are entire talks about the different waves that you can see during a solar flare, specifically, say, sunquakes that you can see over the solar photosphere, and also all the Alpine waves, and they now very recently discovered by the Parker Solar Probe, the switchbacks that we can talk about them in the future in another talk, because that's a little outside the scope of the talk. Now, we have, as almost in any field, a standard model to understand what is happening in a flare. So this is a cartoon that I made inspired by a very standard cartoon that we solar physicists use from Chibata, in which, let me go back a second, you have this light blue color lines here representing magnetic fields. And then you see here, we represent this as very stable magnetic field lines, but then these that stretch out here, they are unstable. And then there is some buoyancy that push these lines upwards. And because of that instability, you get to see reconnection, a magnetic reconnection at a certain point of this initial configuration. So when that happens, there is a release of magnetic energy. Due to that, so there is magnetic energy that gets released and energy conserves. So it needs to go somewhere. And the standard model says that we think that energy goes into accelerated particles in both ways, outside the sun and inside the sun. So for those that are those particles that are being injected into the sun, what they are encountering, they are running into more dense plasma. So because it's more dense down here than up here, when those particles interact with the surrounding plasma, then they emit light via Bremsstrahlung radiation. And I think it's in the next slide. We have run the numbers, and the wavelengths that we expect to see this Bremsstrahlung radiation is in X-rays. That's why looking at flares in X-rays is so interesting and so informative. Sometimes we see that there are also X-rays emitted from here at the tube loop top, and that's an open question in our field. We don't fully understand why that's happening. We need new instruments to look at this kind of emission. And then as a last step, well, there were particles that got injected. There was interaction of those highly energetic particles with the surrounding plasma. So again, energy needs to get transferred. So that energy gets transferred into heat. So this plasma hits, and because it hits, it expands, and because it expands and fully fill the magnetic field lines that we have in the loop, and that's why you see those magnetic loops brighting in UV. Okay, so how to diagnose electron distributions at solar flares? So there are some numbers that we have run, but I'm not going to bring the equations. I brought some cartoons here to give you an idea. So there are some physics phenomena that could account for this. One is synchrotron radiation, but running the numbers, we see that that should emit in radio wavelengths, which is not bad. It means that we need to use radio telescopes to look at this kind of emission. And in fact, we do. Here in California, we have the Owens Valley Radio Telescope Array. And we constantly, well, during the daytime, we look at the sun, and we use that radio data to complement what we see in X-rays and get a full understanding of what's happening. Another possibility of other physical mechanism is inverse Compton scattering, but that's too weak. Same with atomic emission. If we run the numbers, the emission is under 10 keVs, so it's not in the X-ray wavelengths. And when we run the numbers for Bremsstrahlung by collision, that's the strongest emission that we get to see in X-rays. So that's why we believe that we are seeing, in general, Bremsstrahlung collisions or interactions in both what we call non-thermal and thermal emission. Thermal is the same. It follows the same physics of thermalization when you put in contact two bodies at different temperatures, and then you get to see a Planckian distribution. Non-thermal is anything else. In our case, we see power loss. Now, you see, well, there is a ton of different physics that we can learn from looking at the sun in X-rays. And that's where the Padre CubeSat comes into the game. Padre stands for, I didn't choose the name, but it stands for the Solar Polarization and Directivity X-ray Experiment. So that's kind of a stretch for the name, but it's a cool name. It is supposed to be, so we say it in Mexican, like, que padre. Although I haven't heard anybody saying that. And it's scheduled to fly this year. So that CubeSat is a shoebox which contains two instruments. One that is called MEDIA, that stands for the Measurement Directivity to Determine Electron Anisotropy. The TI institution for that instrument is NASA Goddard. And the second instrument that I'm very proud of is SHARP, is the Solar Hard X-ray Polarimeter. If you see that the SolidWorks design is much better, is because that's the one that we work on, and we are the institution, the PI institution for SHARP, and I have the honor to serve as the instrument lead for that instrument, and we are putting it together, and we are having a very stressful time, but things are looking okay. We are still on schedule, slightly behind, but slightly. It's only slightly, but we are gonna make it to launch. We already got a ride into one of the. I'm gonna share that into one of the SpaceX Falcon 9s. So this is the model. This is what we had into the computers, and we made that real. I'm gonna show you in a couple slides. But before showing the actual instrument, why we are working on Padre and SHARP is because when I was showing you the standard model of solar flare, you saw electrons that we believe get injected into lower layers of the solar atmosphere. But the community, the solar community, we don't know if those electrons are being injected as a beam or something else, and that's pretty much poorly understood at constraint. We don't know the directivity of those electrons that are being accelerated during a solar flare. So assume you have the solar flare happening somewhere, and we don't know if the electron distribution during the flare is an isotropic distribution, meaning the electrons get ejected in every direction equally, or if it is something more like a beam distribution. So Padre, in conjunction, basically joining the two instruments, Medea and SHARP, its scientific goal is to distinguish whether the electrons get injected or isotropically accelerated. But I hope is not either of these two, but we find something more interesting, something weird. That's my hope. We'll see. Fully unexpected. So we'll get to see that. Padre that is looking for this kind of problem is not the first instrument that is trying to look at this. I'm actually, I was happy putting together these slides because I know there is another person from your community who has worked on this, Leonard, well known to be also a volunteer here, but also because he worked on Atari, I think, and on the 6502 chip, things like that. I don't know how many people know that during his PhD thesis at Columbia, he helped putting together an instrument, and this is actually from one of his papers, in which they use lithium. We are using beryllium. They use a lithium scatterer here in the middle, and they had 4 different detectors around the scatterer to look at the exact same problem we are looking at, which is the directivity of the electrons. They launched that as part of the payload of at least 1, maybe 2, we can ask Leonard, space shuttles. Unfortunately, they had a couple of problems, and the error bars of the measurements were too big, and the results are inconclusive. So, and since the 70s and 80s, nobody had put together any instrument that look into the same problem. So we finally have the technology to try to do something better, and we are trying to do it. So this concept got transformed into, let me show you, this is the exploded version of the SHARP instrument, the one that we are working at in SSL. So we have, instead of a lithium scatterer, we have a beryllium scatterer. That's this cylinder. You just need to imagine to push this together. But around this main cylinder over here, we have 8 detectors of cadmium telluride using a kind of technology called TimePix that was developed for CERN for the Large Hadron Collider. It's the exact same detector, but optimized to look at the rate and the fluxes that we expect to see from the sun. And this is the whole instrument. And you see here, there are some metal parts that are supposed to work as the shielding of the whole instrument. This is the SolidWorks model, but we several months ago, we passed from a model to the actual instrument. So this is real footage of two of us. That's Brad, a mechanical engineer, and that's me, putting together some connectors for the detectors. The sharp instrument is inside already in that shoebox, which is supposed to be Padre, and is getting ready to be launched. This is from 2 weeks ago. So, well, no, this is from a month ago. So this is inside one of X-ray box that we fabricated and put together to shoot X-rays, polarized X-rays in front of the whole instrument and get to calibrate that. We put the whole satellite inside the deployer, and this is on a vibration table. We are happy to say that we passed vibration. This is 2 weeks ago, and this is when it returns from vibration. So the full spacecraft is still alive and working. Tonight, other people while we speak, they are working on putting the instrument into a vacuum chamber to start tomorrow the final TVAC test of the full instrument. So yes, we are on schedule, slightly late, but we already got it right. We are gonna launch hopefully on June this summer from the Vandenberg Space Force Base here in California on a Falcon 9. So keep an eye open on us and stay tuned, because we'll make the news either as a success or as a big failure. Hopefully it's the first. Okay, with this is enough, Padre. Let's talk about FOXSI. Let's talk about FOXSI. So we said already that there is a lot that we can learn. The sun, if we look at it in X-rays, but we have faced in the last decades a problem, which is many of the very interesting regions on the sun, when we look at them in X-rays, they are a combination of bright parts very close to very faint parts, and these are very interesting. So we need to have an instrument that is able to see both at the same time. We have put together in the past a few instruments that look at the sun in X-rays. FOXSI or Padre are not the first. I just mentioned the instrument that Leonard put together. These are two examples. So we have RESI, which it was the first small satellite funded by NASA and Berkeley, and the space, more specifically, the Space Science Lab was the PI institution, and the head of the solar physics group was the PI. Unfortunately, he already passed away, Professor Boblin. That instrument look at the sun in X-rays. This is the solar orbiter probe. It has 10 or 11 instruments. It has a lot of instruments. One of them look at the sun in X-rays, and this is an example. This is a simulation of the kind of different in brightness that we expect to see in X-rays from a solar flare. So there are two very bright spots here that we call the foot points that are extremely bright, and there are some other regions that are very interesting that show way more structure but that are very faint. When we has this kind of simulated image of how we expect to see a flare in X-rays through the instrument response of either STIX, which is the instrument on solar orbiter, or RESI, what we see is this. So yes, you clearly see the foot points that are the brightest part, but you fully lost the rest. And that's a problem that we have had in the past decades. So we have to come up with a new strategy to be able to see both the bright and the faint parts. So we need to image the sun in hard X-rays with higher sensitivity and dynamic range. And that's where FOXSI comes to rescue us. And FOXSI stands for the Focusing Optics X-ray Solar Imager, and is a telescope that observes the sun in hard X-rays using direct focusing. I'll explain what that means. And is the payload of a sounding rocket from the NASA program Low-Cost Access to Space. So to use direct focusing, you need to use one of two approaches. Either you use mirrors or you use lenses. Let's look at what happened with mirrors. So if you have a mirror in here and you have visible light, and that light is coming to your mirror at a certain angle, you can pretty much reflect that, right, in a specular way. We know that there's no law, it is no law and all of that. But what happens if you try to do the same with a hard X-ray? You have the same mirror and you have an X-ray coming. Instead of reflecting it, you are gonna get that transmitted. So how to reflect that? Well, you can do it. You need to polish that mirror very smoothly and get a surface with a roughness less than 10 microns. That's what you need. And you need to use certain materials. And this is good because I know you guys polish mirrors over here. If you get to those accuracies, please let me know, because I have a job for you. So one, you polish your mirror, and two, you need to use very tiny angles of incidence. So if you do that, then you can reflect an X-ray. Okay, so knowing this is that we use two mirrors. Why? Because we basically, as scientists, go into other talks of other scientists, look for ideas, and I'm pretty sure someone in the X-ray field come into one of these talks and figured that you guys use Newtonian telescopes and that you guys use a primary mirror, which is a paraboloid of revolution, and a secondary, which is a hyperboloid of revolution. And that's exactly what we have, is that idea, just that with the difference that you polish the mirror very much, and then you use small angles. So you get a first reflection on your paraboloid, a second reflection on your hyperboloid, and then you focus your X-ray on a focal plane. But why you use two mirrors when you can use four and not get one but two X-rays? And why you limit yourself to only two X-rays when you can put together a bunch of mirrors all nested together into this, which is called the Volter 1 geometry, but it's not anything different to a Newtonian classic telescope. It's the same math. So this is the main concept that we use for FOXSI. Now we have an optics that is able to focus X-rays down here on the focal plane. Now you can imagine the sun in X-rays emitting a bunch of X-rays. And then you put one of those optics modules. This is an actual photo of one of the modules that we use for FOXSI. And then you designed the geometry of the mirrors. So you put your focal plane behind the mirrors, the longest focal length possible. And for us, is the length of the sounding rocket payload, which is 2 meters. So down here, you put an X-ray detector here. And this one in particular was a silicon detector that we use for FOXSI 1. And then, voila, you get an image of the sun using one module and one detector. But why do you limit yourself to one and one when you can put 7 of them? And this is the entire FOXSI payload that we have put into a sounding rocket. Now I'm happy to say 4 times, and successfully launched to observe the sun. And this is one of those launches. So I'm also happy to say that these are the logos. So yeah, this is a common photo of the rocket that we use. Is a black brand Terrier. This is a 2 stages sounding rocket. This is a Terrier motor. This is a black brand, I think it's 9, and the payload and all the avionics and the logos. So this is FOXSI 0 when it first got proposed and denied. This is FOXSI 1 when we got it for the first time. I was not part of the team at that point yet. I joined the team at FOXSI 2, but I was a student. And then in FOXSI 3, I got the task to do the logos. So you can actually, I hope you can see the difference. And from that point on, I got to design the logos. So that's the FOXSI 4 logo and the brand new FOXSI 5 logo that I actually have some stickers to give you. Yeah, this is FOXSI 5 that got funded. So what is FOXSI? Yes, it stands for that. And it's a sounding rocket payload. It's a telescope that if they ask you, it does imaging spectroscopy of the sun using direct FOXSI. But what that means or why is that useful? It is useful because it can make an image of the sun. And on the background is the standard of, I think this is 304 Armstrong from the Solar Dynamic Observatory in UV. But the green areas are actual X-rays coming from the sun observed with FOXSI. And the good quality that this telescope has is that now you can choose any region, any subregion. If you wanted to make a mask here, you could. For simplicity, we made a square over here, and you can look at the time evolution of that emission. And you see there is some evolution. It's not constant. And you can also make the spectrum. So you can get to see the spectral difference between different regions of the sun. Plus, you can already see that you are able to see bright regions and faint regions all together. So we got it. That image is from the third flight of FOXSI. The first, second, and third flights were all intended to look the sun at quiet times, meaning not large flares. Why? Because we were allowed to launch from the White Sands Missile Range. It's the largest military facility of the U.S. in the U.S. land, and they basically tell you with 2 months in advance, you have to launch this day at this time, and no matter what the sun is doing. So you get what you get. But after FOXSI 3, there was this white paper in which a couple of scientists proposed to NASA the crazy idea of flying solar flare sounding rockets. So what we wanted to do with that was to put together instruments that are optimized not for quiet sound observations, but for solar flare observations. And we wanted to launch on only at the time of a large flare. We got funded. FOXSI 4 was the first, together with High-C Flare was another sounding rocket payload, and SNIFs. High-C is from NASA Marshall. FOXSI 4, the PI institution was Minnesota at the time, and SNIFs was in Colorado. So there were 2 big challenges once we got funded for FOXSI 4. One was to optimize our payload that up until FOXSI 3 was optimized for quiet sun, to optimize that to observe a large solar flare. And 2, probably the more challenging challenge is to catch a flare with a rocket. So for the first one, I'm not going to go into the details unless there are questions, but this is a summary of all the upgrades and all the tweaks that we had to do to the payload just to make sure it was optimized and it didn't get overwhelmed with a large flux of of X-rays coming from a solar flare. But the second challenge was more entertaining, because the second challenge was to launch during a solar flare. And we had to ask ourselves, well, it is feasible to catch a flare with a rocket. This shows the number of sunspots against time, and you see the solar cycle that we have talked about. And this is we produced this plot last week, so it's not fully up to date. But you see that we are at that time of the solar cycle in which there are many active regions, and active regions are they usually host the largest solar flares. So okay, there is a good chance. We run some statistics, and we found that if we were given around 12 days with 3 hours of launch window per day, we estimated some probabilities to catch a large flare as follows. So we were conservative in our original estimates, and we asked NASA to let us launch during larger than C5 class flares. So just for context, flares are categorized by how much emission they emit. I think it's in the 1 to 8 Armstrong band. And then I don't remember the exact numbers. I think it's 10 to the negative 8 for class A, 10 to the negative 5 watts per something, class B, and so on and so forth. So the class A are the weakest, B, C, and then M and X class flares. So there were decent chances. So they let us go. There were so many things that had to be solved, because New Mexico, they said basically no, they were not going to let us fly at any time. They are a military facility. So we had to go to a different NASA facility in Alaska, where they are used to look at the auroras. So they are already used to just put the rocket together, start the countdown, and wait and hold until they see an aurora. The difference now for them was to put the rockets together during the daytime and be ready to launch during the daytime. Anyways, so we had to put together a bunch of tools to we are trying to avoid the word predicting, because we are not predicting, but we are giving early alerts of a large solar flare within minutes of, okay, there is a large flare coming. And that's what we put here. So this is the challenge we had. I told you there were NASA found 3 payloads: FOXSI 4, high-C flare, and SNFs. When we were putting together the rockets, unfortunately, SNFs, the payload from Colorado, during the vibration test, one of the mirrors fell and broke. And that was painful. That was really painful. So we were down to 2 rockets, high-C flare and FOXSI. And here we are. In the photo is not everybody involved. But if you count, and you can count, there are 90 people in the photo. And this is a photo just a couple of days before the actual launch, with the 2 rockets behind us. Don't worry, the rockets are not cubes. They are just, we had to put styrofoam around them, because Alaska is chilly. But they were ready to launch. And so this was the first ever sounding rocket campaign, and we had like this, intended to observe a large solar flare. So no pressure. So the FOXSI and the high-C goals were, if you look at the mission in time, these are hours at any arbitrary start point. In the soft X-ray, in the mission that I was telling you how we classify X-ray, we classify solar flares in the 1 to 8 Armstrong. So you see that it is it's background, 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 and at a certain point, it jumps, and we wanted to observe emission of the sun at a time in which the ghost class flux was larger than a C5. So roughly like there. This is kind of a cartoonage because it was inspired on data, but cartoonage. So yeah, this was the FOXSI4 goal, and Hi-C didn't want it to see the what we call the impulsive phase, but they wanted to see the decay phase. So different goals, but complementary. So that was good because we got to see the beginning of the flare with FOXSI and the last part of the flare with Hi-C. And we did. So this is accelerated because otherwise I would have you here like for a few hours just to look at this. But this is the launch of, I think I put the 2 rockets or only FOXSI, probably only FOXSI. So you see, this is for sure FOXSI, oh, the 2 rockets and Hi-C. So FOXSI was launched first and then Hi-C second. We were able to do this with what we call now the Frozen movie. You'll see why. It's, we put a bunch of tools together, but this we proved we have a minimum viable product to anticipate a large solar flare. So what we did was to use data, the closest to real-time data. So basically the ghost X-ray flux that has a cadence or like time granularity of 1 minute and a latency of 3 minutes. It means the latest data point that you can get right now is how the sun was 3 minutes ago. And we also use EVE data on the Solar Dynamic Observatory. So we are very used to use the pretty images of the Solar Dynamic Observatory, but that's not the only instrument that it has. It has a way more useful instrument, which is this ultraviolet quad cell. It looks at the sun in the 0.5 to 7 nanometers, I think, wave range. The cadence is much better, also the latency. And the SDO, the other instrument, the beautiful one, with the AI images, the latency is not good, it's 5 minutes. But it was useful to know where the sun was having the flare. So we put together a full Frozen movie. Here are the people involved, grad student and postdocs, and myself. We call, because she, who is Marianne, who is a grad student in Minnesota, she named all the tools as Elsa, Anna, Christoph. I forgot the other characters of that movie, but and the good thing, she's so creative. She found really good names that actually stands for something useful. So anyways, the product of that whole set of tools, it was the Go. So when you put together the rockets, every subsystem have to give the go so the rocket can get launched, and one of the goals is science. So we have the power to look at the sun, look at the activities that we were monitoring in all these screens, and then hit the final go. FOXSI was a success, and there are some preliminary results. Something fully unexpected is that you probably can recognize from the logos that I have to say, I designed that during the FOXSI4 logo during the pandemic. I made this Fox when the pandemic started, way before we launched FOXSI4. But a nice surprise is that when you put together the X-rays that come from the flare that we observed with FOXSI, we actually saw the logo. So that was very, very spooky and unexpected. But these are also very preliminary results. On the background is the 304 Armstrong image of Solar Dynamic Observatory. And here in purple each is the X-rays integrated image in 0.5 to 5 keVs. So you can actually also see a little bit of that, the head of the fox in here. This is a movie. No, it's not a movie. No, it's not a movie. But this is a little bit of how things were looking during flight at the time of the launch. this box over here, one of our Japanese colleagues put it here. So you see, you get a bunch of feelings during the campaign. Sometimes you get bored and you do fun stuff to keep you entertained. Oh yes, each dot in here is a photon. It's an X-ray that we observe from the sun. So we successfully launched the payload comes down to Earth using a parachute. It had a very, I'm gonna say, fun slice over the snow in Alaska. And then a helicopter goes, rescue it, bring it back to us. We put it together into crates, got it into a truck, got it back into the Space Science Lab, and the payload is resting in one of our labs. That's a student that is working with us this summer. So once we got it back, we were also proposing to get a fifth ride, because FOXSI 4 was fresh, entertaining, so much fun that we wanted to do it again. And we proposed again, but this time having Berkeley as the PI institution, and I'm honored to serve as the PI. And it was selected, and it's scheduled to fly this winter. We are putting together everything to make this happen again. We'll see how it goes. So keep your fingers crossed and stay tuned. We have 3 minutes. I got authorization to show you the behind the scenes of what the FOXSI 4 campaign was. So something unexpected that happened was that we were working crazy there. And then certain people from the Smithsonian Channel showed up and say, hey, we heard that you guys are putting together a rocket to look at solar flares. And yes, they run the authorizations and they got to film all the behind the scenes. And they finally released the episode. It's funny because they usually do things about how crazy it is to operate the airports and military base in Alaska. So the full program, if you call it, is called Ice Airports Alaska. And there is an episode in season 5 called Sunspot. And this exaggerate a little bit. Oh, okay. And I think with that, what happened? Oh. Yep, that's all that I had. So thank you so much. And if you, I'm on every social media platform, Facebook, Instagram. You can follow me as Astronomy Milo. I try to post some of the things that we are doing actively at the lab now with Padre and with FOXSI. So thank you all again for coming and for your time.
Thank you, Milo. Anybody who is in our audience, both present and on Zoom, feel free to ask questions. I don't see any from Zoom yet. Dave, do you have questions? Gentleman behind you. I get to go first. I'm purposely avoiding.
Why do you use sounding rockets instead of putting a satellite in orbit to measure the flares?
That's a good question, and I hope you ask that question to NASA because we really want to put a permanent spacecraft out there. That's the quick, funny answer. The real answer is that NASA has this program that I showed called Low Cost Access to Space that has basically 3 main platforms. It has sounding rockets, it has stratospheric balloons, and it has CubeSats. The 3 platforms are supposed to be ways to get into space with new technology that has never been in space before. And the idea is to increase the TRL. And once you proved that that new technology is able to survive the space environment, then the idea is that you can submit your whole idea to have a permanent telescope with the same technology that you used. We did that already. We submitted already twice. We have both at both times we got rejected. Last time it was very painful because we got the highest score, and the reason was programmatic reasons. It was because FOXSI and Solar Prof, the kind of science that they could do together, it is limited compared to the other mission that was competing against us. So they decided to put that. Is also an amazing mission, and it's Lockheed Martin, I think, is the PI institution. We are not giving up. So we are actively putting together, and we hope even stronger case for the coming round. Every Friday we meet to just work on that. But yeah, the idea is to have a permanent FOXSI in space, looking at the sun using this technology. Yes, yes.
Dave, you have a question?
I have 22. 11 or
11 by 11.
Okay, that only gives me 2 questions. So I've got to figure out which questions are really, really good here. One question is, God, can I have a few more than that? Okay, thank you. How deep is it called the tackle line?
The tackle client.
Tackle climb. How
Yes.
deep is that?
It is supposed, if it exists at that depth, it's supposed to be at the 70% of the solar radius. So if solar radius is 700,000 kilometers, so basically multiply that by 0.7, and that's, well, 0.3 if you want to go.
Okay, I'm going to do that in freedom units.
Yeah.
And again, I'm going to round off because I think it leads to clarity for those of us that aren't solar scientists.
Right.
The approximate diameter of the sun, I know it's not really this, but it's about 1 million miles,
Okay.
which means the radius is 500,000 miles. And you said it's what percentage of a radius?
So 70% coming from the center out.
So 0.7 times 5 is about 350,000 miles out from the center of the sun.
Right.
And how thick is it?
It is very thin compared to any other region. So if I had to give an order of magnitude, it's probably a 1% thick of the solar radius.
1%?
It's very thin.
Are
It's
you
extremely
kidding
thin.
me?
And it's supposed to be there. There are many things that happen at that discontinuity region. So for one, the energy, we believe, according to the models, the energy gets transported in different ways. So from at the very core of the sun, there is the core of the sun, which goes from the pre-center to 0.25 solar radii. It ranges between 0.2 to 0.3, depending on who you ask. And from that point on, we have the radiative zone, which is called that way because energy gets transported via radiation mostly. Then at the tackle line, the energy starts to get transported via convection. So that's the reason, we believe is the region of the sun in which the convective cells get created.
Oh, I
right?
see.
And the bosons up to the surface transporting
So
the
the
energy.
the tackle client is the interface between the radiative zone and the
Convective zone.
convective zone.
Right.
Got it.
So that's one thing. And the other thing is, up until the tackle client, we believe that the whole sun rotates as a solid body, meaning it rotates at the same speed. And only starting at that depth is that it starts rotating at a differential rotation. And 3, we believe that the main component of the magnetic field is generated there. Now, it is an open problem. It's called the solar dynamo problem. If you ever get to hear a talk about a solar dynamo, if you really want to ask the key question, you should ask how they believe the very first magnetic fields get created. Because all the models work if you have a first dipole that is already running. But starting from nothing to something, I haven't seen any model that is able to do that, for one. And 2, there are other solar physicists. I like to explore crazy ideas. or like out of the box ideas. And this is not totally out of the box, but some physicists believe that there is more than one main dynamo, that there are multiple dynamos. I could see why and how, because you get the convective zone, right? And then there is another discontinuity zone, which is the photosphere, in which the radiation gets to stop being transported mainly by convection to again be transported by radiation. So it's not they are not totally wrong, I would say, but it is a controversial topic. It's like you should see like those discussions. It's fun to see and hear.
I can imagine. Gosh, I have so many questions. Oh, I wanted to ask your opinion. When do you think Solar Max is going to be? What you're seeing?
You know, running the numbers last week, we are at the peak already right now.
Right now.
Right now, I think for us, for the technical applications of launching rockets and doing missions that involve high solar activity, I would say it's promising mid 2027. I think that's when solar activity is going to start declining.
So between now and mid 2027 is
right.
the window of opportunity for you.
Yeah.
Yeah. Rebecca and I are thinking of doing an Aurora trip.
Oh, you do it. Oof.
Yeah.
I got to see them for the first time in Alaska. That was the best gift, actually. Like, that's not included here, but after we launched the rocket, it had a flare, right?
Oh, wow.
So it emitted energetic particles, and a couple of days after, they arrived to Earth. So they generated an aurora. So we got to see the aurora generated by the flare that we observed with FOXSI. So that was like the cherry on top of the cake.
Oh, that's wonderful. As I recall, the University of Alaska has a program, and this is where they do the launches from,
Yeah.
isn't it?
Yeah.
And I think I saw on one of the slides, it's called Poker Flat or something like that.
Range. Yeah.
Where is it?
Research range.
What is it?
It's Poker Flat Research Range. It is at I am blanking the city.
Anchorage?
Fairbanks.
Oh,
Thank you.
yes. Okay. Okay. Gosh. Okay. For those of the people in the audience like me who don't remember the difference between soft X-rays and hard X-rays, what is the difference?
Ooh, you asked the key question.
I'm sorry.
It depends who you ask, and it highly depends the context. So kind of like mid-ground answer. It highly depends on the size of the flare that you are observing. For large flares, the discontinuity is around 20-25 kiloelectron volts. That translated into Armstrong, I think like less than an Armstrong for sure, but I will need to look at
So an angstrom might be considered the dividing line between soft and hard X-rays.
Yeah.
So
probably around.
shorter than 1 angstrom, hard X-rays.
Right.
Longer than 1 angstrom,
For-
soft X-rays.
For large flares.
For large
but
flares.
if you go to small flares, then that division, I have seen it going down to like 8 kiloelectron volts. If you go to nano flares that are the tiniest solar flare-like phenomena, then that line gets really gray. Like it highly depends on the context of what you are studying.
So this touches upon another one of my questions, which is, what is the range of wavelengths that you're observing in X-rays?
Yes. So we have 7 telescopes. That's good because then we can optimize each one to different energies. So like when you see FOXSI as a whole, we can say that we can see X-rays from 0.5 kiloelectron volts to up to 25, 30 kiloelectron volts if you stretch. The highest part of the energy range, we are constrained by the focal length, not by the detectors. We have detectors that can easily go over 100 kiloelectron volts. But it's the optics. We need very long focal length. That's why we need a permanent FOXSI, and we are limited to 2-meter focal length in the Sound rocket. But for the spacecraft, we are proposing, we already proposed 12 meters. Now that I told you we are meeting to consider new ideas, we are even considering doubling that value. So a focal length of 24 meters.
Wow.
It is not the final. Right now, we are targeting more. The most likely scenario is something like 18 to 20 meters in focal length, and that's gonna give us up to like 80 kiloelectron volts, 100 kiloelectron volts.
Wow.
Oh, yeah.
I don't want to monopolize. Does anybody else here have any questions for the moment? Okay. Okay, I got it. Can I keep going? Okay, sure. A couple more. Okay, I got to try to shoot here. Oh, okay. Alrighty. Oh, shoot here. Cost of one launch.
It varies from rocket to rocket. I have to say, the solar rockets, I learned we are among the most expensive between the 4 different divisions that they have. If I have to give an average number for the payload only, is around 5 million for the solar
For one payload.
For one payload. That's not counting on all the avionics, all the NASA subsystems. We don't have full access to that cost because it's out of our hands, and that's probably kind of.
So you don't know what that full cost is?
No.
They won't tell you?
They probably won't tell me, even more likely to me because I'm a foreign national. So probably I know there are things that they keep away from me.
You might be a spy.
Right.
For the Colombian space program.
Yeah.
Okay.
Oh gosh.
Okay. A couple more. I found it fun, the styrofoam. It never occurred to me. Okay, you guys have the styrofoam on there. I assume you remove the styrofoam.
No.
Before you don't?
No.
You leave it on during the
Yes.
launch?
Yes. So it's a styrofoam. So during the launch, that's one of the reasons why the launch from Alaska looks so spectacular compared to the launches from other places. And it's because we had to use so much styrofoam. But that's also, you see flame flying around when you run those videos in a slow
Do you use
motion.
styrofoam from White Sands?
No, oh yes, in White Sands we also use a styrofoam,
Huh.
but only around the payload section.
Okay.
Same reasons. It's basically to keep it thermally isolated. I have mixed feelings about that because so far we have survived. They do that very standardly now for almost every payload, as I know. But the reason I say I have mixed feelings is because we are ESD protected, so you want to minimize the chances of getting a spark somewhere. So far it works, so it's fine. As long as it works, we are good.
That's hilarious. Let's see. Oh, launching in winter for FOXSI. Why in winter? Is there special? It's just the window of opportunity?
It's yes. So it is still an open and continuous negotiation. We are gonna launch from White Sands this time.
From where?
White Sands.
White Sands.
In New Mexico. So I told you that's the largest military base, yes, but they finally agreed on working with us on trying to find ways to launch. They are not gonna, so for FOXSI 4, they gave us 2 full weeks in Alaska to launch every day. We went vertical, blah, etc. From White Sands right now, what we are negotiating is they're gonna give us 3 full days, the same launch windows in terms of hours per day. But then we are forced to stop and leave and come back in a few weeks. And if we haven't launched the first time, and try another 3 days. If we didn't launch, repeat 4 cycles.
I assume you're leaving the rocket in place. You're not forced to remove the rocket.
Yeah, well, that's also part of the current negotiation. The most likely scenario is that we are gonna leave the rocket on the rail, but temperature, humidity control, and all of that
Yeah.
for the weeks that we are away. Yeah, but
Do you want me to stop? What Oh,
You could
I can, that's right.
You could actually talk to him. You're in the same room.
That's right.
Yeah. All right. Well, thank you, everybody.
Thank you, thank you.
Oh, yeah.
Thank you. Okay, I exit this.